All right, everybody, for today's video, the topic is factor theorem or remainder theorem. All right, busy, gotta go, let's get after it. So for each example, prove d of x, the divisor, is a factor of f of x using the factor theorem. So the factor theorem says, f of x has a factor x minus c if and only if f of c is 0. So very simply, to use this prove this using the factor theorem, we need to plug in the 0 of this divisor 1 into this equation and evaluate. So you're just plugging in, you're remembering to plug in kind of the opposite of what you see here, so the 0 of this, which is 1, and when we do that, we've got 1 minus 1 plus 0, which is equal to 0. So by the factor theorem, since f of 1 is 0, therefore x minus 1 is a factor. Now why did I say the factor remainder theorem? Because, by the factor theorem, because I think the factor and remainder theorem are so closely connected that I always kind of just describe them together. The remainder theorem says we could have also answered this by dividing f of x by d of x and seeing if there's a remainder. Something is a factor if and only if when you divide by it there's no remainder. The remainder theorem says if we were to have divided this by x minus 1, the remainder would have been f of 1, which is 0. So factor and remainder theorem are basically the same thing. So we'll do this one next. The if it's going to be a factor is determined by whether f of 3 is equal to 0 or not. So we plug in the 0 of the divisor into this polynomial, 3 cubed minus 3 squared minus 3 minus 15, and then evaluate. Let's see how quickly we can evaluate. We're going to do this in parts. And look, right there. Therefore, x minus 3 is a factor by the factor theorem. Okay, that's it. I'll go back and explain now and maybe add some detail. So when I teach the factor remainder theorem, it's when we're talking about factoring polynomials. Makes sense, right? And to be honest with you, really factor remainder theorem isn't that helpful if we compare it to the other tools we have for factoring, in my opinion. The one place it's helpful for is when you have the 0 of 1. If the 0 is 1, I think factor theorem is helpful because when you plug in 1, really what you're doing is, when you plug in anything into a polynomial, you're raising it to powers many times and then multiplying by coefficients. But when you raise 1 to any power, it stays as 1. So really, when you're checking if x minus 1 is a factor, you're plugging in x equals 1. When you do that, you're really just adding the coefficients. So I can tell right away that 1's going to be a factor here because my coefficients are 1, negative 1, 1, negative 1, and those coefficients add to 0. So basically, again, you know, the factor remainder theorem is really helpful in terms of efficiency when you're checking the 0 of 1. Now let me finish this off because the way this is helpful is if we go back here and we take this polynomial f of x equals x cubed minus x squared plus x minus 1, I want to actually completely factor this. So if I know x minus 1 is a factor, I know I can do synthetic division with a 0 of 1. So let me do that right quick. Oops. So what does this tell us? This is more evidence that, like we said, x minus 1 is a factor because we actually got a remainder of 0. So what that tells us is our original function, f of x, here can be factored as x minus 1 times what this is. This is x squared plus 0x plus 1. So we factored the third degree cubic polynomial into a first degree times second degree. Now to completely factor it, we would try to factor this second degree polynomial. Is 1 a 0 of this? No, because if we add the coefficients, 1 plus 0 plus 1, we get 2. So 1 is not a 0. And in fact, no other real numbers will be zeros because couple ways we could look at this. One way we could look at this is, once we have a quadratic, really just use algebra 1 skills to factor it. And if you think of x squared plus 1, that's not going to be factorable, because if we verify this with the quadratic formula, a is 1, b is 0, c is 1. So if we look at the discriminant, b squared minus 4ac, 0 minus 4 times 1 times 1, the discriminant is negative 4. And if you remember from algebra 1 and algebra 2, the discriminant is negative means that this actually has no real solutions. It has 2 non-real solutions. So actually, we can say, for our purposes, if we're factoring over the real numbers, that's our final factored answer. If there was another 0, we could have divided this by another 0 and kept breaking it down. But for now, that's our answer. And we use the factor remainder theorem as part of our toolkit. All right, keep asking questions, keep factoring those polynomials. There's more tools I'll add to this toolkit. But as always, go blue.